This walkthrough explains the main machine learning techniques used in artificial intelligence, from core categories to practical model building. You will also see how learning approaches, tree methods, perceptrons, support vector machines, and Bayesian ideas fit together. Machine learning is a subset of artificial intelligence that enables systems to learn and improve from experience without explicit programming. Its importance lies in automating decision-making, pattern recognition, and prediction. The material highlights uses across healthcare, finance, and robotics. 3 machine learning methods explained. The content groups machine learning into supervised learning, unsupervised learning, and reinforcement learning. Supervised learning uses labeled data to make predictions. Unsupervised learning finds patterns in unlabeled data. Reinforcement learning learns through interaction with an environment to maximize cumulative rewards. Supervised learning trains models on labeled datasets so they can predict outcomes for unseen data. It is suited to tasks where input and output examples are already known. The source presents it as a core category for building predictive models in artificial intelligence. Several supervised algorithms are named. Linear regression models relationships between input and output variables. Decision trees use a tree-like structure to make decisions from feature values. Support vector machines find an optimal hyperplane for classification tasks. Unsupervised learning works with unlabeled data. Its aim is to analyze that data and discover hidden structure or clusters without predefined answers. This makes it useful when you want the system to uncover organization, similarity, or patterns on its own. The source lists 3 unsupervised methods. K means groups data into clusters based on similarity. Principal component analysis reduces dimensionality by identifying principal components. Density-based spatial clustering identifies clusters from density and can handle outliers. Reinforcement learning involves an agent that interacts with an environment and learns through trial and error. The goal is to discover actions that produce the best long-term outcome. In this approach, learning is guided by cumulative rewards over time. 3 reinforcement algorithms are highlighted. Q-learning is a model-free approach that uses a Q table to learn action values for states. SARSA updates values while considering the next action. Deep Q networks combine reinforcement learning with deep neural networks for larger state and action spaces. Logistic regression is presented as a supervised learning technique for binary classification. It uses a sigmoid function to model probabilities. The material gives medical diagnosis, fraud detection, and customer churn prediction as applications, showing its value when the outcome has 2 classes. Kernel methods are described as algorithms that implicitly map data into higher dimensional spaces to solve nonlinear problems. A support vector machine using the kernel trick is given as an example. Applications include image recognition, natural language processing, and bioinformatics. 020-30-405. The comparison is direct. Logistic regression is simple, interpretable, and suited to linear problems. Kernel methods are stronger for nonlinear problems. Their trade-off is computational cost, which can make them more expensive than simpler linear approaches. Inductive learning generalizes patterns or rules from specific examples or data. The process begins with data collection, then pattern identification, model creation, and evaluation on unseen data. The result is a generalized hypothesis that maps inputs to outputs. Deductive learning derives specific conclusions from general rules or existing knowledge. Its process includes knowledge representation, reasoning through inference mechanisms, and output validation. The material gives expert systems as an example, where rules and known facts are used to infer new information. These approaches differ in input, output, and method. Inductive learning uses data and follows a bottom-up path toward a generalized model. Deductive learning uses rules and facts and follows a top-down path towards specific conclusions. Together, they support both prediction and logical reasoning. Classification and regression trees are explained through the structure of decision trees. Nodes represent decision points based on features. Branches show possible outcomes of decisions. Leaves hold final predictions, either class labels for classification or continuous values for regression. Information gain measures the reduction in entropy after a split based on a feature. The Gini index measures impurity in data splits and is used to determine the best feature for classification splitting. The material links classification trees to fraud detection and spam filtering. Regression trees are used for predicting continuous values such as house prices or sales forecasts. Their strengths are simple interpretation and support for categorical and continuous features, but they can overfit and struggle on highly imbalanced datasets. Perceptrons are linear classifiers that use weights and bias to separate data with a straight line or hyperplane. They are simple to implement and computationally efficient. Their main limitation is that they only work on linearly separable data. Multilayer perceptrons extend them with hidden layers and nonlinear activation functions. Support vector machines are supervised learning algorithms that find an optimal hyperplane to maximize the margin between classes. They can handle linear and nonlinear data through kernel functions. The source presents them as more versatile and robust than perceptrons, while noting their computational demands on large datasets. A prior is an initial belief about a parameter. A likelihood reflects how well a model explains observed data. A posterior is the updated belief after new evidence. Applications include spam filtering, diagnosis, text classification, sentiment analysis, and fraud detection. The practical example is handwritten digit classification using the MNIST dataset. The objective is to classify digit images, and the dataset contains 70,000 images of digits with 28 by 28 pixels. The workflow covers loading the data, converting labels, splitting training and test sets, normalization, model training, evaluation, and sample testing. The material says the model typically reaches about 92 to 95% accuracy and suggests convolutional neural networks, data augmentation, and hyperparameter tuning as extensions. Together, these techniques show how artificial intelligence systems can learn, reason, predict, and improve from data.